Okay. Who has hand sanitizer? Can I get a couple volunteers to sanitize their hands and then just pass these out? Everyone? Thanks. Remind me your name?
I'm Hayden.
Hayden. Okay. Oh, great. Nice to meet you, Hayden. Here, I'll even take some of that too. Sorry. Great. Thanks. Yeah. You just sanitize, help Hayden pass these out.
I got your text.
Oh,
but I
hey.
just saw you.
Yep, here I am. Come sit in and you can have fun with us in linear algebra.
Okay. Thank you for the offer, though. We appreciate it.
No worries. Thanks. No news about your mission call, huh? Okay.
I was expecting that next Tuesday, but yeah, no wait.
Okay. Oh. Don't stress. How's everyone's weekend? Not long enough? So, too long? We couldn't wait to get back into linear algebra? So the kid that was just here, he's my son, he's a freshman here. He's expecting his mission call any day. If it doesn't come today, it'll be next week. So, yeah, it is exciting. So, who did the best thing on yesterday to celebrate Labor Day? Did some? Oh, it was so nice to watch BYU dominate in the game. So they look really, really good. Hope we can keep it up. So, yeah. I mean, last year Navy had an amazing quarterback and helped them out tons. And so they do have a new starting quarterback. A couple of years ago, I just thought this was a cool story. Navy was playing at home. They dressed 2 or 3 quarterbacks. All of them got hurt. It was like one of the first games of the season. The 3rd or 4th string quarterback was sitting in the stands. They had to go get him and say, "Hey, go get dressed." He came out and he won the game for them. So, what a day! He was king for that. King for the day. All right, let's get started. Who would like to offer a prayer for us? Any volunteers? Thank you. Say it nice and loud.
We can understand the things that we studied today. We can get all of our work done and be good students and be good sons and daughters. In the name of Jesus Christ.
Amen. Thank you. We had a neat experience in the last class. One of the students in the last class is Muslim. He's from Jerusalem, lives a few blocks from the BYU Jerusalem Center. And that's how he ended up here. He would always go there and do things. He's done concerts there. I had him pray. He gave a prayer in Arabic, a Muslim prayer. It's not an official Muslim prayer, but that was really cool to hear him do that. Okay, announcements. Let's talk about a few things. Well, let's do this first. Homework. So everything you need to know. So the homework that's assigned today. So prep for 2.2a. So you're going to watch the videos or study the slides for the first part of 2.2. If you do the slides, you do all of them up to a slide that says row reduction algorithm. So you don't have to know that for next time. Read the first part, page 64 to 68 in the textbook, the first part of 2.2. Do the online section of 2.2. And then do the written 1.3 and upload it to Gradescope. 1.2 you can now upload to Gradescope. So we didn't get that information out really early, but put it in by midnight tonight. So any questions about this? About your assignment for today? Okay. If you do end up quarantining, or if you're just really lazy and you don't want to come to class, I'm just kidding. Come to class. If you don't have a health reason, you need to come. So, I know you don't need to, of course. You have your agency, but please come. Here I'm on Learning Suite. I'm on the Zoom links for office hours and class. So this first Zoom link here for my office hours, that's the same Zoom link we're using for this class. So we had a couple people in the last class that had to Zoom in. So if that happens, you know where to go. You don't have to email me. You can email me, but I'll just assume you're quarantining if you're Zooming in. Okay. All right. Any questions not about linear algebra, just about the class or homeworks or handing in things, anything like that? Logistics? Okay. Porter, do you want to pull up? Never mind, I got it. So I'm going to walk through a few of these things. That doesn't help. Whoa, that helps. Okay. I'm going to talk a little bit about each of these, okay? And then I'm going to ask for questions on 1.3. So if you have questions on 1.3, get them ready. Here we have equations of lines in R2, lines and planes in R3. So if you haven't picked this up yet, R2 is the coordinate plane. It's because we have a real number line crossed another real number line, kind of like the real number line squared. R cubed, you've got three coordinates, in space. So you're already familiar with the general form, ax plus by equals c. These other forms, you might not be as familiar with. This normal form, it's hard for me to interpret, especially in this form. It's easier for me to interpret it as a dot product. So, yeah. So here you have some vector cross a normal vector minus a point. I wrote this the wrong way, didn't I? Should do this one. Okay. So this is a normal vector, which means if it's this is normal to a line. So if this is n, then we want to describe all of the points along here. If this is P doesn't have to be the base here. P could be anywhere. And then any of the points along here, these could be any x values. Sorry, I should write that bigger. These could be any x values. X minus P, any of the x values minus P is going to give you a vector, right? Like this. And then if I dot that with the normal vector and get 0, then I know that x coordinate is on this. So this is where they start, and then you do this, and then you pull the n minus P over to the other side. So this vector form turns out easy to write. So here you have x equals a point plus t times a direction vector. I don't know if you'd write p as a vector. P is a point here, but it is like they have it bold because it's multivariable, right? It's not just a number, it's a packet of numbers. So if I want to write if I have a point 2, 0, and I have a vector 3, 1, vector 3, 1, okay, then I can write the equation of that line. You guys already know how to write down the equation of the line if you find the slope with using the 2 points. Although this isn't a point, this is a vector. This is more closely related to the slope. But one way to write it down is take my point, write it as a vector in standard form, standard position, and then add t times 3, 1, where t is any value, any real number. This is like the number of servings. This is a food. This is my current intake for fat and protein. So this would tell me all of the possible values I can get out, all the possible diet values I can get out if I have one food with two nutrients. I can think about x this way, or I can think of my outcome as an x and a y. So this vector here represents your all of your unknowns, whether 2 or 3 or however many. So okay, so I go 2, and for every value of I'm at 2, 0, and then for every value of t, I increase my x by 3 and my y by 1. So over 3 up 1, over 3 up 1, over 3 up 1. So, okay, and then Porter, can you slide over, please, so I can see the parametric form? Other way, yeah, thanks. Let's hear it for Porter. I don't know if you can see it. I think he's remote somewhere. So, I love technology. Okay, never mind. No one knows where that song is from? It's Napoleon Dynamite, the marriage scene. You guys got to watch it. All right, okay. So this parametric form is a vector form, but you've expanded out your vectors. So Instead of x, you write them down as xy. Instead of calling it a vector, a point P, you write down the coordinates 2, 0. Like P1 is 2, P2 is 0. So 2 plus 3t, 0 plus 1t. You just break it down and write down the whole, each equation separately. So these are close to each other. Just from here to here, you just start writing down things in packets. So keep your packets together. All right, let's go. The vector form. Yeah, we'll do vector form here. This is of a plane. Notice the vector form of the line here in 3 dimensions. It's exactly the same as the one here in 2 dimensions. What's changing, though, is that here x only has 2 components. Here in R3, it has 3 components. So, but this works for any dimension space. You can still write a line, even if x, p, and d had 20 or 70 or 100 components. So that'd be the equation of a line in R100. So this vector form here, let me try to explain what that is, or how to think about that. If I've got a point, P, and I've got a couple vectors, U and V, as long as they are linearly independent, then I can talk about all of the possible points in that plane, and by how to get there from point, by starting at this point and how many U's it takes and how many V's it takes to get there. So all of the possible points are X bar, or you can think of it as X, Y, and Z. Oops, didn't need to put that in brackets. Just bracket happy. So, in the same way with the vector form of a line, I can start with a point and then I can change along one dimension with, as long as I have one vector. Here you just have 2. So you can start with a point and then you can have S of U's and T of V's. And any combination of these will tell me how far out I go here or here, and how far up I go here or here. It's kind of like a grid. You can think of it as a grid with U's and V's. So, so if I want to get to this point, I say, well, I'm going to start at P, and then I'm going to go 2 U's over, so S would be 2, and up 1 V. And so that gives me a point. We'll do a specific example of this later. So, but yeah, this is like, if you do the food examples, U and V will give you the components of the food, and S and T will tell you be the serving sizes, and P tells you what your current intake is. So if I take 2 servings of U and 3 servings of V, then that'll tell you the total, what your new intake is for your food on whatever nutrients you have here. Okay. One important thing on the general form. So the general form, oops. This, I missed this key point, and it caused some pain when I was in your shoes trying to do some homework problems. It mentions it in the book and it uses it in some examples, but I want to emphasize it because it's really important. If you have this equation, there's a really easy way to find a vector that is normal to this plane. A really easy way. You just write down the coefficients. Okay? This A, B, and C is normal. This vector is this is a normal or perpendicular or orthogonal, they all mean the same thing, vector to that plane. Yes? Nope. it actually works with lines. So if I have x plus 2y equals z, equals 5, okay? I'm only dealing with this in R2, right? So if I go up 5, then my slope is going to be y equals a minus 1/2 x plus 5 halves. So I'm right here. So if I go over 1, I go down. If I go over 1, I go down 1/2. Okay? So my slope is a minus 1/2. Well, what's perpendicular to a minus 1/2? This slope. It's going over 2 and up 1. Yeah, over 1 and up 2. The slope of 2. So this, this vector 1, 2 is perpendicular to this line. And I tried to give an explanation of the way that I think about it to the last class, and it just confused everybody. So I'm not going to try it this time about why, but I'll give you the really short version. If you change x here, like if you increase x by 1, you have to lower y by 1/2. So if this goes up 1, here you have to go down to minus 1/2. Because you have to do some canceling out here. For this to always equal 5, if you increase 1, then you've got to change the other one. And these coefficients affect that change. And because of the canceling out, you get a normal thing instead of going in that direction. But don't worry about it if it doesn't make any sense to you. Okay. All right. Questions that you guys bumped into on 1.3? Yes. 68. Oh, that's from 1.2, right? Yeah. Send me an email and I'll put up a video or have one of the TAs make a video that walks through those. Okay. Great. Good question. Other questions? If you don't ask me questions, I'm going to give you guys questions. Okay. So here we have a pyramid problem. If you didn't get one of these worksheets, raise your hand. So you may have come in late. Anyone need one? Okay, we have a couple back there. Go ahead and start working on this. Just spend a few minutes doing as much as you can, trying out what you can, and then we'll start going through them as a class. Okay? You are welcome to work together. Just please maintain social distancing. Okay? So it is okay if there's a lot of talking going on and you have to be loud. That is okay. So if you have a question, ask your neighbor or raise your hand. I'm happy to come and help. But yes, this is yours. You can write on it. Yep. It is easier to do a vector equation on number 1. Okay, so I'll give you that as a hint. So.
Brother Corey,
Yeah.
Is this worksheet available on Learning Suite or anything for those who are remote?
I have to say flip because if I say flip, my kids hit me. So kind of like in the best 2 years. I'll take a picture of one and I'll email it to you, Porter, and you can put it up. I meant to put it up before class because I knew there would be people that were zooming in. And I apologize. Okay, Porter, I just sent it to you. I feel like I'm in Star Trek and I can just like, I'm talking to the ship, like the computer, and it just talks back. And so. So take 2 more minutes. I know you're not going to get all the way through this, so just do what you can. Back on. Okay, there's about 20 different ways to do these problems. Okay, you can pull on lots of fields of mathematics and a lot of stuff that you know to do these. So if you did it differently than me, that's okay. Also, I know that you might get stuck doing these. That's okay. The reason that I have you do them is so you can bump into something that you don't know. So when we go through it, you can either ask the question or be looking for it as we go through it. So, okay. So I'm going to do this, I'm going to do one with the vector equation. Vector equations are easy to write down. They're not always insightful or easy to work with, but they're easy to write down. You're not supposed to tell students that something is easy, because then if it's hard for them, they feel bad. So I didn't mean to come across that. They're easier than other forms, like the general form. So I'm going to do my best to just draw the front of this pyramid. Okay, it's front face. This is 0, 0, 0. This is point A. This is E. That's 1, 1, 2. And this is B. It's 2, 0, 0. Okay. To write down the vector equation, I just need the vector equation of a plane. I just need one point in the plane. We have 3 easy ones here, but I just need one. Someone pick your favorite point of these. 0, 0, 0. Okay, nice. We'll pick the origin. 0, 0, 0. Just for fun, I'm going to do this twice so we can see the difference. Okay, so I'm also going to pick E. So 1, 1, 2. Okay, so I can pick either of those. Now, these are going to be 2 equations. They're going to look different, but they're going to describe the same plane, all the points in that plane. I do need 2 vectors, okay? 2 vectors in the plane, okay? So a vector, sometimes you think of vectors as a points, but more usually we think of vectors as a change in location, not a position. A change in position, not a position, okay? So a vector needs to be a change. So one vector is like that, the line right there, that vector, or this vector. So the vector that goes from A to B, or the vector that goes from A to E, both of those are vectors in the plane. Okay. How would I write down that vector that goes from here to here? What are the coordinates, or what are the packets of numbers? It's just 2, 0, 0, and you might think like, but Brother Corey just said they're not points. Well, really, I'm doing this. I'm subtracting the 0, 0, 0 from that to make that a vector. So since it's in standard form, if I recognize it in standard form, I'm like, oh, I can just use the coordinates as the vector, okay? But we're not always working with points in standard form. So 2, 0, 0. What's another vector? 1, 1, 2. Oh, I should use color coding here. Should have done that. Well, too late. Okay. So 1, 1, 2, because 1, 1, 2 minus 0, 0, 0 is 1, 1, 2. So, and then I put my parameters in here. S and T. So this describes all of the values, all of the points x, y, and z in this plane. Like not just the part that's on the pyramid, it would extend out. If we continue that plane and extending it out, then like an infinite sheet of paper, an infinite whiteboard, like this would describe all of those values. You give me any s and t, and it'll give me an x, y, and z. This might seem a little weird. You might think like, Brother Corey, you're just getting an x. No, this is a vector. This is a packet of numbers, which is really, that's representing my x, y, and z. That's representing all of my coordinates. That's a packet of coordinates. Okay, so at s equals 2 and t equals a minus 1, I would get, what, 4 minus 1, so I could get a 3, 0 minus 1, so I get a, what do I get, 3 minus 1, and minus 2. So I can just pick values different values for S and T, real numbers, and then do the addition to figure out a point, and that point will be in that plane. So it's one really nice thing about vector equations. They're really easy to find points on the planes. Yes?
Did we just solve the spread, the second term as 2s 1, 0, 0? Or is that bad syntax? Or
2s, I'm not sure if I quite, so 2s,
and then the vector 1, 0, 0.
oh, 1, like this? You could do that. No, that's equivalent. That's just fine. So using what we know about vector algebra, you're just good. You're still fine. Okay, let's do this one, because this one might throw you off because we had that origin here. I'm going to pick two more different vectors. I'm going to pick this vector. That's still a vector in the plane. And I'm going to we'll pick this one going backwards. Okay, those are still two vectors in the plane. There are 2 points in the plane, and I get the vector that goes from one to the other one. So this would be, so I'm going to call this BE. That goes from B to E, and I'm going to call this one EA. Sports. B, grateful. Okay. So right now, think in your head or write it down. What are the components of this vector BE? Silently, yeah, do it in your mind.
So it can be any vector. It doesn't have to be from E to A and E to E.
It can be any vector any two vectors as long as they're independent in the plane. If I did the AB vector and I did double the AB vector, I'm only going to be still stuck on that line. I need to have some vector that's linear independent from that vector. So, good question. Yeah. Provide the midpoint of those, which, yeah, you just cut all those in half, those coordinates in half. Yeah, that's good. Okay, how am I going to find this vector BE? I'm going to subtract. Which one do I start with? B or E? So there's an easy way, like, if you're not sure, you can start with a really simple example and say, okay, I'm just going to start with 2, 0, 0, and call that B, and I'm going to go -2, 0, 0. Call that something like C. Which one's BC and which one's CB? Well, this is easy enough for you to figure out. What I'm going to try is, if I subtract B minus C, what do I get? So, sorry, B minus C is going to get 2, 0, 0 minus a -2, 0, 0. So I get 4, 0, 0. Which vector is that? Is that the one going this way or the one going this way? It's the one going this way. So I subtracted C. You subtract your tail, you end up going to your head. So subtract the tail. That's what we found out here. So nice trick on the test. If you can't remember, do a nice, really simple example like that. So I'm subtracting my tail, right? Yep. So I get a minus. Can't do arithmetic. I never was good with numbers. Okay, -1, 0. Oh, see, told you. I'm just, testifying. So 1, 2. So there's a vector. So I could use that vector over here. A -1, 1, 2. -1, 1, 2. And then how about EA? So I'm going to do E to A, I'm going to subtract E. So A minus E, A is 0 minus 2 minus 1 minus 1 minus 2. Okay. And then S and T. These are parameters. You need any value. These are like the serving sizes. You just pick any value of the serving sizes, and then you add those up, and you'll get 3 coordinates on that plane, X, Y, and Z. Okay. Questions about number 1? Or anything we've done here? Yes. Oh, if S equals, what did I say, 2, and T equals a minus 1, then you get 3, a minus 1, a minus 2. If I did my arithmetic correctly, but that's now in doubt. So, okay. All right, other questions? So you can quickly get to your parametric forms. Okay. Can you slide over so we can see the parametric forms? Porter, thanks. So these parametric forms, they are simply the vector form, but just expanded. Okay, so if you start writing out each of your components, and you can see I've already started to write out some components here of mine. So we're just one step away from writing these down. I take my X as X, Y, and Z. Then I can just start writing that top equation. X equals 1 minus S minus T. Boom, I've got, and then you can just write those down. So that's one thing. And you can, and once you get this, you do know a couple vectors in your plane, and you do know at least one point that you can just read right off. Okay? So it's a nice place to start. The general form is harder, and I don't know if we'll be able, holy cow, I don't know if we're going to be able to get there today. Okay, what is the equation of the line K? So K goes from B to E. So that's the equation of that line. What is the equation of the line that goes, that B and E lie on? Let's see if you guys can write down the vector equation of that line. Okay. Vector equation is the easy one to write down. Can you write down the vector equation of that line? And if you can write down the vector equation, can you write down the parametric equations? You have to do a little bit more work. It's not super straightforward. And if we don't get it today, I'll make a video of it and put it up online. Yep, you're welcome to talk to each other. So. Okay, so here's two possibilities if you're doing vector equations. So if you're doing the vector form, I have a point. For one of them, I picked B. For one of them, I picked E. Okay, and it does not matter. So that's a good question. Does it matter which direction the vector is going? It does not matter because you can change the dot sign here to get to that same point, right? So one of these I picked as B going to E. We had already solved that one here. The other one I just picked the opposite direction of that, E going to B. So change the sign, boom. Any point on those I can get from these equations. I can pick some t and it will equal, for some t I can get any point on that one. Okay, now the harder one. Find the equation of the line through the origin that intersects line K at right angles with K. So, right K there. So I'm looking for a line that goes here and is perpendicular. I want to know what the equation of that line is, and I also want to know what that point of intersection is. So what do we know about things that are perpendicular? What tools do we have to work with when we're trying to do things that are perpendicular or orthogonal or normal? Okay, dot product. So when we're dealing with perpendicular things, we should think dot product. What else? There's something else. The what? Sorry? The normal line. So if we can find a normal line, so perpendicular, so normal line or a normal vector. If we could find a normal vector to this line, then we could find we could use something and try to make sure it goes through that point. Great. So if we can find a normal vector, what else do we have? That has to do with perpendicularity. Yes? Unit vectors? Unit vectors they're not just with perpendicular things. They're just vectors of length 1. So gotcha. So if we do the dot product with unit vectors, then we can figure out angles of things much more easily. Okay, I see where you're going there. So there's one other thing that really deals with perpendicular. Projections. One nice thing about projections is we have a nice explicit formula for it. So if I want to find the projection of u onto v, then that is u dot v. What?
That was a question, but why is it projection of u onto v but written? It looks like projection. That's just.
Oh. Yeah, I think if v is the bottom one that u is going to go down onto. Okay. So, and then the dot product of v dot v times v. So we have a nice explicit formula for projection. So if we have a situation that deals with perpendicularity and we can think about it in terms of projection, that can help us out a lot. You can rewrite this also as the norm squared. Sometimes you can do it this way. Oops. I don't like when we use it. I should have used A's and B's because my U's and V's start looking like each other. So, okay. So is there a way to think about this problem as a projection? We can project AB onto K. So here I have I'm going to rewrite it over here. So here I have AB. Here I have K, which is also, we can think of that as BE, right? And so who said Good. How are you thinking about the projection? That's right. If we project this perpendicularly, it will help us to find this point. It doesn't give us that point, it gives us this vector. But then if we add that vector to the point B, then we will have that point. Okay? So now if we can write down BA and BE, then we can just use this formula for finding those. So what BE we already have, it's right here. What's BA? BA is a minus 2, 0, 0. Yeah, so, yeah, I don't know what happens, yeah. Maybe it'll work both ways, I don't know. Okay, so now we can just write it out. Because really what we want to get is the projection of, we're going on to what? We're going on to BE, and we're projecting BA. So I take the dot products of those. So minus 2, 0, 0, dot, what's my other one? A minus 1, 1, 2, and then a minus 1, 1, 2, dot, a minus 1, 1, 2, and multiply that whole thing by a minus 1, 1, 2. I think it does matter which direction they're going. So, yeah, did I do it the wrong way? So, okay. So this is the vector BE, right? This is that vector. And our projected is going to be a scaled version of that vector. This is just ends up being just one number. The dot product here, just a number. The dot product there, it's a number. And we just take the ratio of that. So we derived this in the peanut butter book. And the textbook also talks a little bit about it. So what do we get? So here you get positive 2, 0, 0. So here you get 2 over, here you get 2, I'm sorry, here you get 1 plus 1 plus 4, so you get 6. And that's just 1/3 times a minus 1, 1, 2. So a minus 1/3, 1/3, it's a positive 1/3, and 2/3. That is the vector. That's the vector that goes from here to this point so that these two things are perpendicular. What's the point? Part of what the problem we're working on is what's that point? Well, we just have to add this point to, add this to B, which is 2, 0, 0. So this is the point, 2, 0, 0 plus a minus 1/3, 1/3, 2/3. Add those together, and you get 5/3, 1/3, 2/3. So there's your coordinates for that point. And now we can write down the equation of the line in vector, because now we have that point. We had a point before, but now we can get the vector between them. Yep. So yeah, so we can just subtract 0 from that, which is just that. So we could just write down that equation as x bar equals the point 0, 0, 0 plus t 5/3, 1/3, 2/3. So because this is a vector, I'm thinking about it as a vector in standard position that goes, oh, no, wait, yeah, so that's the point. Yeah, that's the coordinate. So thinking of the vector in standard position, we'll go from there to there. So if we did that right. Okay, questions? So we found a vector that goes from here to here, but that's not the coordinate. The coordinate, I have to add it to what I started with. So this coordinate here, B, is 2, 0, 0. So I added those, and so the 2 minus the third is 5/3. So good question. All right, I think we're at time. Have a great day.